Yeah, here in India, the coastal towns are experiencing cooler temperatures, while the inland is getting warmer. It started
Yes.
getting warmer here again.
Yep. Yep.
Yeah.
I was just thinking today that I have been to India and Bangladesh
Oh, okay.
1980 40 times.
Ah, okay.
So tonight is my 41st time.
Okay. Yeah. Thank you very much for that. Yeah. Yeah.
No.
Yeah. Many thanks for accepting our request. Yeah. It's a pleasure to have you on our webinar. Yeah.
No, I enjoy these things. They're good. I learn a lot.
Yeah. Just a minute. Yeah. Last night I got a mail from Professor Brian Hoskins.
Oh, yes.
Yeah, he's keen to know the timings, the local timings. I said 9 o'clock in the morning IST means 4:30 will be the British Standard Time anyway, GMT.
Yes.
Yeah, early in the morning. Yeah. Perhaps if it is not convenient for him, I'll send him a recorded version of your lecture.
Yeah, he's a good friend of mine.
Yeah, yeah, he has been saying that. Yeah, he has been saying that. Okay, good morning, ladies and gentlemen, audience from India and abroad, and also students of Andhra University's Department of Meteorology and Oceanography. I have much pleasure in kicking off the second phase of our webinar. The first phase has been started with the inaugural lecture by Professor Sir Brian Hoskins. And the second phase is being again kicked off by Professor Webster, another Rossby Medal winner. And to introduce Professor Webster in brief, Professor Peter J. Webster is a professor at the School of Earth and Atmospheric Sciences and the School of Civil and Environmental Engineering, Georgia Tech, Atlanta. And he did his PhD in 1972 from the Massachusetts Institute of Technology. And then he started his career as a postdoc fellow at the Department of Atmospheric Science, UCLA, United States. Thereafter, he became an assistant professor at the Department of Atmospheric Sciences, University of Washington, Seattle. And then he was a visiting professor at the Tata Institute of Fundamental Research during the period 1981 to 82. And he was then an adjunct professor at the Department of Mathematics, Monash University, Australia. And then he's now a professor emeritus at the Georgia Tech. Professor Webster had many honors and awards. Notable of them are the Juchi Charney Award from the American Meteorological Society, the National Science Foundation Special Creative Award. He is a fellow of the Royal Meteorological Society, the American Meteorological Society, and the American Geophysical Union. He has been the recipient of the prestigious Carl Gustav Rossby Research Award from the American Meteorological Society in 2004, and he has been an outstanding faculty research author award from the Georgia Institute of Technology. Professor Webster has been a member of many committees, and then he has many field experiments to his credit, and he has rendered many invited lectures, and he has produced 22 PhD graduate students And then 4 people are currently pursuing PhD under him, and he has more than 25 book chapters to his credit. And notable among them are his 119 publications in various reputed journals. Okay, he has been an editor of the Encyclopedia of Atmospheric Sciences, the guest editor of the JGR, Atmosphere and Oceans, and he has been editor of the Tauber volumes of 1995, and he's been a chief editor during the period 1983 to 1986 for the prestigious Journal of Atmospheric Sciences journal. With these few words, I invite Professor Peter J. Webster to give his talk. Professor Webster, yeah.
Professor Ramakrishna, thank you so much. I think it's interesting to me to think back, getting my PhD in 1972, that probably most people listening to this talk weren't even born then. I'd like to pretend I was only 14 when I got my PhD, but that wasn't the case. So what I'd like to, one of the interesting concerns to me over the period of my career has been the monsoon. And I've been trying to understand the variability of the monsoon from many perspectives. And what I'm trying to do here today is try and consider the monsoon as part of the general circulation. And to do that, we need to do a little bit of dynamics, but I'd like to tell the story first about how the tropics and the extratropics have tended to communicate. And it's not always been the considered view of science that they communicate at all. And many people thought, we have the Hadley circulation and we have Rossby waves, and somehow they're not connected. So what I'll do today is try and tell you how they are and what that means for monsoon variability. Now, the picture you're seeing now is the summer variability of the potential vorticity field and high up in the troposphere. And it's very chaotic. And you'll notice that, you'll notice that in the monsoon region, it looks rather benign with things circulating around it. And those circulations, those filaments, are going to be extremely important in understanding the variability of the monsoon. So the issue of extratropical interaction, early on, if you look at the top right-hand diagram, there was a thought that we had trades, we had Westerlies, and somehow they were joined together by conservation of angular momentum, but dynamically we didn't understand. And the equatorial regions was dominated by this zonally symmetric Hadley circulation, the second diagram. And one of the problems is that we have a conundrum because the nature of tropical phenomena is very different from the nature of the extratropics. One is a divergent circulation. The second is Rossby waves. So how are they connected? So what we'll try and do is see if there are some simple physical constraints. And will this help us be able to do better in understanding the prediction, the phenomena of the monsoon and bettering its prediction? This is the tropical rainfall variability. On the left-hand side, the variability of tropical rainfall by frequency, 2 to 10 days, 10 to 20 days, and 20 to 60 days. I didn't include the long-term variability. That's a different lecture. But what you see is that there's an enormous amount of variance in the 2 to 10 days. I'm sorry, I don't have a scale here, but the darker the color means the more of the variance. And when you look at the monsoon region, there's this peculiarity of very strong variability in the 10 to 20 and the 20 to 60 day variability. And the diagram on the right shows you a nice spectrum of the Bay of Bengal precipitation. One of the dominating features, and everybody in the tropics knows, is a diurnal variation. And then we have this peculiar bi-weekly order 10, 15-day variations of convection. And it's not really understood. And to the right of that is the intraseasonal variability. And if you look down below in the bottom right-hand corner, what you see is the variability. This is from a wavelet analysis, and it shows the three variations: the diurnal variation, the background, up and down, up and down, up and down, the biweekly, the dark curve, and the intraseasonal. And you'll notice that they're synchronized. You're not getting biweeklies when you don't have intraseasonal. And the diurnal is emphasized during the peak of the biweekly and the intraseasonal. That turns out to be rather important. So when you look in details at the intraseasonal variability, where we spend a lot of time trying to understand it, on the left is the classical Sika-Gadkul diagram. I'm an enormous fan of Dev Sika, who recently passed away. And he was one of the, how can I describe Dev as a down-to-earth, pragmatic, very, very good dynamicist. And Sika and Dev and Sulachana Gadgil came up with this diagram. It's the first one showing the maximum cloudiness zone along 90 degrees east, all the way up through the Bay of Bengal, showing the northward migration year after year of the maximum precipitation, the trough, and convection. And it's rather interesting, isn't it? Because what you see is that most of the time you have one band propagating northwards. Occasionally it reforms in the south, and that takes over. On the right-hand side is the central Indian precipitation for a number of years. That's the red area in the middle of the Indian continent there, subcontinent. And what you can see is an enormous amount of variability, interannual variability. Actually, interannual variability is rather small, but the variability within one season is very large. You can see that in the bottom diagram. And these are pentads, but you can see up and down, up and down, up and down. The background curve is the annual cycle. So the idea being that if you can somehow predict those intraseasonal variabilities, in other words, if you go to the left-hand diagram, be able to predict when you are going to have an excursion of the precipitation over central India or wherever it might be, what an enormous boon that would be. 2002 is a very, very interesting year. That's the bottom right-hand diagram. And it started off as a good year climatologically. The onset over all of India was very, very correct. Then all of a sudden, the monsoon ceased. And what didn't reassert itself for about 2 or 3 weeks. And the idea is that if one could have forecast that variability, the enormous loss of agriculture and livelihood by people would have been avoided. So the great goal of monsoon meteorology is the prediction of the intraseasonal variability. I'm not going to spend too much time talking about that today, but I really think it needs to be mentioned more often. Just a couple of theories. One is the surface hydrology propagation, where the monsoon rising motion feeds back to advance itself going northwards. And a lovely theory by Simon Dingham in England shows that the top diagram shows an active monsoon where you have outflow from the Mascarene High, crossing the equator, giving abundant rainfall into India. But somehow, if you have a disturbance of the Mascarene High, the surge of potential vorticity is such as to turn the flow away from the equator towards the equator and crossing the equator, and there is no precipitation. So there are many theories. I think all of them have an element of truth, but we haven't quite put it all together yet. I'd like to talk about the discovery of the Equatorial Westerlies. I'd like to talk also about the fundamental work of Herbert Real, an amazing scientist. He raised many questions that challenged theoretical studies. Theory, by the way, stated that you couldn't have vortices in the upper troposphere that weren't locally generated by in situ instabilities. And this thought, I think, held back tropical research and understanding for a number of years. But, you know, with all theories, one has to work through these things. Here's some of Riel's earlier work. So much, hardly any data, but what he found in the first was extremely steady trade winds, hardly varying, very little synoptic variability. Whereas, and you can look at the bottom right-hand diagram, shows the steadiness of a function of time of the winds in the lower troposphere. But he also found that there were extreme regions of, strong equatorial tropical westerlies. And you can see those in the bottom right-hand diagram where you go from trough, ridge, trough, ridge, trough, ridge, trough. Now, this didn't fit with the standard theories of how the tropics and the extratropics interacted. So these trains of atmospheric vortices, they seemed unattached to the rather undisturbed lower troposphere. How can that be? And here's what Herbert Riel said. The intermittent appearance of high tropospheric westerlies on the equator is a foreign thought to the classical view of the general circulation. But there is evidence which he has shown that they do occur. This flow in the high levels is unsteady, coupling at high latitudes between the circulation of the northern southern hemisphere. And this is an enormously deep statement, coupling between the northern and southern hemisphere, and an intrusion of tropical, extratropical type disturbance into the heart of the tropics. Now, this is really heresy at those times, but we all know it's very, very true. Now, Giulciani, of course, was an amazing scientist. And his idea was that, well, okay, from a theoretical point of view, you could have the interaction between the extratropics and the tropics. Waves could propagate towards the equator, but only those waves which were very, very long could propagate into the tropics. Alas, they didn't have much energy. And so what we had then was the view of the tropics as a zonally symmetric circulation, strong easterlies and to the north, westerlies and to the south, westerlies. And so that held us back for a long time. Mankin Mack and John Young, using zonal symmetric models, showed this to theory of Chinese, gave some support. But the wave propagation theory just didn't work. So when satellites provide us with a new view of the tropics, this is the 500 millibar potential vorticity, potential temperature diagram and the OLR anomaly, just one day. And what you can see is that you have very zonal flow, and then around the certain regions of the tropics, the isotropes tend to nudge towards the equator. Now I will add, and this is by the way that these isotropic perturbations go deeply into the tropics. Now I would add that if you were to use isobaric analysis and not isentropic analysis, the Westerly ducts would be discernible, but you'd find, you would find that the isobars were almost parallel. So understanding, one needs to use analysis tools that are fit for purpose. And as you'll see throughout the talk, isotropic analysis is very, very important. But just to show you a couple of diagrams, that this is on the left-hand diagram here, this is the 200 millibar U versus the perturbation energy. And you see here are easterlies and very low perturbation energy, but where you have the westerlies in the mid-Pacific, strong perturbation. So idea being that perhaps there's an excursion regionally of the tropics. And here's just a scatter diagram showing the same thing. And Jim Holton and I played around with this, had some fun with some simple models, and we took, whoops, here we go, very touchy. We looked at the zonal, what something like the climatological westerlies and easterlies, and here is the westerly region in the tropics. And we thought, what about if we moved perturbations back and forward? And what we found out is that, you could have propagations from one hemisphere to the other by Rossby waves if the Rossby waves were in the right position. So this is called the westerly duct, which will raise its head a number of times. Now, I want to just move a tiny bit to potential vorticity. I mentioned that we have to do things isentropically. And the left-hand diagram here shows you the vertical structure of the isentropes. And what we see, of course, is strong variability in the tropics. So what we're going to do is compare the upper tropospheric potential vorticity and the lower potential. So here we have the upper tropospheric potential vorticity. Let me see where we are here. Yeah, this is the upper tropospheric here. And what you can see is that the variations of potential vorticity are very strong in the equatorial regions where we have westerlies. But below the westerlies, there's very, very little variability. And so somehow waves are propagating, but they're not creating great disturbances in low levels. And what we can do is take a cross section through here and just see what it looks like in terms of wave propagation. And here we have, this is now 3 days before we have maximum variability, and you see these negative, positive things moving towards the equator. And here, and they're riding up above these, what we call the easterly dome. And so it's quite possible to have propagation into the equatorial regions, just like Riel said, and we understand why it occurs. It's interesting too that this is consistent with the Charney theory. If you were to just consider easterlies, the waves aren't propagating, but when you consider westerlies, they do. So this is all very neat, but we have to ask the question, what produces the near stationary westerly ducts? Now, TUTs, by the way, which I haven't defined, are upper tropospheric troughs. So here we have in January what the 370 degrees Kelvin climatology is. That's roughly about 200 millibars. We have jet streams, we have easterlies, we have a westerly duct. And in July, the time we're going to spend most time talking about, we have westerly maxima, and also a second one here, an easterly jet, and we have this trough through here. If you were to look at these in cross-section, these are the westerly ducts in June, July, and August, which is the bottom one here, and these are the ones in December, January, and February. So what I'd like to do is look at the climatology of the 370 degree K or 200 millibar potential vorticity. And I'm going to look at the Asian monsoon variance. I'll talk very briefly about convection in the East Pacific. So the same diagram again. This is now July, and you'll see here filaments of potential vorticity moving down across India. Look where they start. They start here in the mid-Pacific and move down, down, down. And where do they start? These are the waves of the westerlies, and we have to work out why the hell we get westerlies here and watch them move down, 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 down. So these filaments turn out to be rather important. And we can sit here and watch these all day. They're very beautiful. You can also go to the southern hemisphere and see the waves moving through. Now this is negative potential vorticity. And you can see the waves propagating back. Now, I'm going to argue that much of the variance of the spectra over India is caused by these chaps moving through here. So let's go back and look at the variance in the 10 to 30 wave band, and and what we can find if we, oh dear me, looking at the potential vorticity variations in this box here, get maximum, minimum, maximum, minimum, max, 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 and so on. And we'll see if that's associated with variability on the monsoon rainfall. Same diagram again. I have to apologize that some of these diagrams are out of sequence because about 3 hours ago, some nasty animal raided my computer and rendered all my PowerPoints impotent. So what you're seeing now is sort of a hodgepodge. So 10 days before maximum excursions here, what we're going to see are a sequence of geopotential anomalies, green negative, pink positive, and they're going to move through here on the 850 millibar wind. So here we go. And you can see them moving through. These are the filaments. Notice the trajectory. Oops, let me go back one. The trajectory is down through here. So what's causing these? Where are they coming from? And you know, it's somewhat of a foreign thought for many of us to think that here we are in the southern Indian Ocean, but things are raiding and causing great variations from all the way up here at 50 degrees north. So this is just one sequence for 10 days, 15 days in June. And the left-hand side is the total potential vorticity, and you can watch these filaments move through, move through, move through, move through. These are the perturbations, and you can see here once again, perturbations moving through. So you might think that if you're a forecaster in India or Pakistan or Thailand, that you're going to have to look a little broader in the tropics, the extratropics, be able to understand the variability of things occurring in the tropics. 20 years ago, that was a foreign thought. Still a foreign thought for many people. But I wonder if we can run with that and learn something. This is the Boreal Winter. These black lines here denote the 2 westerly ducks. And you're going to see that just like in the northern hemisphere, these you can see now filaments coming back over Australia. Oops, there we go. I apologize for this. But the excursions from the northern hemisphere, it's interesting. Look, you can see here, you get the filaments now, but they're not going around the monsoon anticyclone. They're moving more into the Americas. And these variations, by the way, for if you're interested in the strange term called atmospheric rivers, these are breaking Rossby waves, and they have a lot to do with the variability over the United States. But we're concentrating today on the monsoon regions. Oh, just to show you what these things look like, this is some nice work by Fanutu and War, and they show the 200 millibar geopotential and 350 K IPV. That's a sequence, and you can just see how that changes. This is the OLR rising motion, giving all types of convection. So what we have then is tropical, extratropical convection. And what I'd like to suggest that this is through coupled divergent and Rossby dynamics. So what we have here is it's a January. I don't particularly want that, but Michael McIntyre, one of my great heroes, described the polar vortex as a wave turbulence jigsaw puzzle. And he said the regions of strong PV gradients where oscillatory modes would dominate, and also regions where the Rossby waves break. And so he was considering mainly a little to the north of where we are. So here's the jigsaw puzzle, and Michael McIntyre and Haynes are going to put this together for us. So Rossby waves breaking in the westerly ducts lead to advection of equatorial PV fluxes, and the divergent circulations of the Hadley circulation, or the monsoon if you'd like, lead to the advection poleward of jets. And these are related. Now, forgive me, I'm going to quickly go through a couple of theoretical slides. Anybody who's interested in this can contact me, or I can give you the references where these are detailed. So, potential vortices, oh dear me, is conserved only in adiabatic frictionless flow. And we're looking at regions where diabatic heating and dissipation is important. So Michael defined this thing called potential vorticity substance, and which we won't need to go into, except to say that between, they're the two, McIntyre and Haynes, look very serious. And so what we can say, if you go through all of the theory, and we won't tonight, or this morning, that the zonally average advection of this potential vorticity substance equals 0. In other words, across a latitude circle, this advection here is going to average to 0. And this is a very, very important, it's called the Impermeability Theorem. And we can learn so much from the work of Haynes and McIntyre of understanding this. We've taken their theorem and tried to expand it in 2 papers by one of my students, Sebastian Ortega, and some other work I've done. But the important thing is that we have this constraint. So if you look at the observed fluxes on the 9th of July 2001, why that, or the mean fluxes. And what you find is that the mean fluxes across 30 degrees north are almost equal. North versus south, north versus south. So what we find that here we have a northward advection and here we have southward advections. And somehow they balance out. And here in January, similar type of thing. The flux of potential vorticity substance is almost the same within the errors of our calculations. So this is pretty important. So let's consider a number of ideal situations. We can look at a symmetric circulation. You might be aware of the Held and Howe zonally symmetric model, which really helped us understand a lot of things. But it turns out not quite correct. So what it says, if you have a symmetric circulation, that you either get northward or southward advection of potential vorticity. And only if you have an asymmetric circulation can you have a balance between this northward and this southward advection. So the important thing is that the potential vorticity flux equals 0. So let's see what happens if the system has no heating. That's what we have. Let's add some heating to the system. And now here's the heating, and we have a northward flux of potential vorticity, and whoops, let me go back one. And we have to have a southward flux somewhere around the latitude circle in order to compensate, to honor the potential vorticity theorem. So the Westerly duct serves to return the potential vorticity system, substance to the equator, thus satisfying the impermeability theorem. So the important thing is that, notice here, that the northward flux of potential vorticity is concentrating the isotropes, if you'd like, concentrating the isobars. So that means this is a jet stream. So this is a place that becomes unstable, and Rossby waves propagate into this region. Now, perfect Rossby waves are just going to go sailing around. They're not going to transport preferentially potential vorticity to the south, towards the equator. So something else must be happening. This is just an example of breaking Rossby waves that in a little experiment we did. When a Rossby wave is said to break when the potential vorticity contours are irreversibly deformed, leading to a mixing of the potential vorticity field. So something in this region here is deforming the Rossby waves as they form and move to the east. Now, monsoon meteorology, why the hell do we care? Because these are the guys are producing the filaments of potential vorticity which go across the south of India. This is just an experiment showing the breaking Rossby waves and the potential vorticity. I don't want to go into this, but there's very good reason why the Rossby waves break. That here's the Rossby waves. It's the jet stream caused by the northward flux of potential vorticity, by the divergent circulation of the monsoon. Rossby waves form, and they move into a region, and we can argue very strenuously that the deformation of that Rossby wave, like here on the right, is severe, and the Rossby wave breaks. When it breaks, it's potential vorticity flux towards the south. I might add that the same principles can be used to account for the great cloud bands of the southern hemisphere. This is the South Pacific, oh dear me, the South Pacific convergence zone, and what we have is a great region of deformation here, and the Rossby waves go into here, they break, and they create an excursion of potential vorticity towards the equator. So these great cloud bands are nothing special. They're the same as the westerly ducks in the northern hemisphere, just look a little more dramatic. So here's a summary, if you'd like, of how the monsoon and the extratropics interact. We start off by having an ocean atmosphere, ocean land differential causing a circulation, a direct thermal circulation. That's transferring potential vorticity north. By the way, I don't have time, but if anybody's interested, one should ask the question why the monsoon rains of the Indian monsoon are so much further north than the monsoon rains of all the other continents. And that has to do with the elevated heat source. Some beautiful work by Alan Plum showed how you have to have the elevated heat source in order to have precipitation so far to the north. If the Himalayas were shorter, I'm afraid that India would get a lot less rain. Shorter, I mean lower. India would get a lot less rain. There's some beautiful work by Peter, my goodness, showing that when you look at the sediment in the Ganges and the Brahmaputra over tens of thousands of years, that it wasn't until the Himalayas got to a certain height that you got sediment. In other words, that there was not sufficient rainfall prior to that. And the elevated heat source is very important. But we'll take it as it is. We have a direct circulation. It creates a jet stream which becomes unstable. The Rossby waves are produced and move into the region where we have, where we have distortion, breaking, and they produce equatorial flux of potential vorticity. And this, of course, feeds in to the loss of potential vorticity by the divergent circulations in the equatorial regions. So we have a nice conduit here. It's rather a strong dynamic This is all due to the Haynes-McIntyre interpretation of the impermeability theorem. So if we can think of that then in terms of trying to understand, this is now 345 K upper troposphere, and we have transports northward, transports eastward, transports southward by the divergence circulation and the Rossby waves. It's the only way we can explain these large values of IPV in the equatorial regions. Same type of thing. So how do we utilize this stuff for predicting monsoon variability? Well, here's that sequence I showed you before of 370 K PV. You see these filaments moving. What one can do, of course, in a synoptic prediction, is to create IPV fields. Very important. You can't get away with using isobaric analysis. It's going to fizz away to nothing. And you can follow the filaments across the South China Sea, over India, and you can make a prediction. They provide sort of an empirical 5 to 10 day prediction. But what about numerical prediction? Well, you need a global domain. Number one, this is long-term, and variations longer than 2 or 3 days mean you have to have a global domain. You need to create predictive IPV fields, and you need to follow the disturbances, and you need ensembles, as these phenomena are terribly nonlinear. So you can provide a probability of precipitation variability. So this is the type of interesting diagram here that when you look at this is time going northward. So if you look at 15 to 25 degrees north, and this is the potential vorticity, and you see that this is now in the Indian Ocean region, that the potential vorticity is going from east to west across the Indian Ocean, and further south you get the same variability. Other times of the year, the variability goes from west to east. But during the time where you're getting the divergent circulations, creating unstable Rossby waves and an active westerly duct, this is the type of situation you have. So there's a lot of ammunition here for diagnostic studies to understand the variability of the monsoon. Now, just let me see what time I have. Can I have a few minutes here? And I'd like to talk about, does this mean anything in terms of understanding the whole globe? We've spoken about the impermeability theorem for the Northern Hemisphere, but it doesn't say anything about the whole globe. I'd like to suggest, it's a nice piece of work by Graham Stevens and co. And what they show that despite large differences in geography and climatology of the Northern and Southern Hemisphere, the annual top of the atmosphere radiation balance is the same between the hemispheres. This is here within 1 or 2 watts per square meter. Models go all over the place, but the annual north-south flux difference between the 2 hemispheres is almost the same. And when you think about it, the 2 hemispheres are awfully different. This is the relative area of land and ocean, and lots of ocean in the south, lots of land in the north. Why should they be the same? At the same time, when we look at the annual volume of precipitation, land plus ocean, that between the 2 hemispheres, average over the year, 6.8 by 10 to the 11, 6.68 by 10 to the 11, almost indistinguishable given the errors of the data. The precipitation in the 2 hemispheres is almost identical, even though the precipitation over the ocean is very much greater in the southern hemisphere, and over the land is very much greater in the northern hemisphere. So I've sort of wondered a little bit, this is just a better diagram of that, the annual average precipitation by volume. The difference is 2%, 3%. That here's the land annual average precipitation, the ocean precipitation, land plus ocean, almost the same. So I think, we're very, very lucky in many respects because very, very strong theoreticians have helped us. Brian Hoskins, of course, in his understanding of potential vorticity, gave us a new way of thinking about the dynamics of the atmosphere. And I think, the Haynes-McIntyre has advanced that too, because it places severe restrictions on planetary scale motions. And this is a very strong property. And I think, as we stand back and think about where we are in meteorology, I think we're, thanks to Brian and to Michael McIntyre and to Haynes, that we're in a better place to understand than we were, for example, prior to the work of Herbert Real and the work of Jewel Charney and the corrections thereafter. So this is very exciting. So what we've done is consider the heat source, find out, doesn't matter, isotopes will concentrate in the device of circulation, and substance we continue to transport it away from the tropics. We get unstable jet stream, and we get a transport potential vorticity back to the equator, completing the circuit. And this works on an interhemispheric point of view too. And I think, in a sense, that when you look at Graham Stevens' work of the constancy from one hemisphere to the other of the radiation balance at the top of the atmosphere, and when you look at the stuff we've done on the constancy of precipitation rate and also total volume, there is a constraint on the circulation of the planet. And I think that Haynes and McIntyre have helped us understand that. This is just the interhemispheric stuff. So thank you very much. I hope I didn't go too quickly, and I apologize that the goblins got into my computer sometime today, and I had to scurry to get a presentation together. Thank you. Hello.
Yeah, thank you very much, Professor Peter Webster. I have a few questions from the audience. Yeah. First of all, yeah, Professor Ashok conveys his greetings and good morning to you, Professor Ashok from Central University.
Yeah.
There is a question from Dr. Mohan. Is there any rationale to bandpass the data with a 5 to 30-day filter?
I'm sorry, could you repeat the question?
Yeah, is there any rationale to bandpass the data with a 5-30 filter, 5 to 30-day filter?
No, it is rather arbitrary.
Okay.
I think the reason we did that, when you look at the Bay of Bengal spectra, and you see there's a concentration in the bi-weekly to intraseasonal variability. I think we're trying to isolate the bi-weekly variability. It's rather an arbitrary choice, and one could play around with it. The data's there. My goodness. I would be so excited now to be a student with all this data. You can get from Eastern WF all the IPV data and play around with it with any type of filter that you would like. It's very exciting.
This is a question from a student. What are the main reasons for the Rossby wave break?
I had to skip from that because that's a complete talk. But what happens if you imagine having just zonal westerlies of constant speed, and you generate a Rossby wave for whatever reason, it goes sailing around, sailing around, sailing around. But now let's think about if we don't have constant westerlies, but we have strong westerlies, and then we have weak westerlies. What's going to happen to that wave? So we spend a lot of time trying to understand what happens to a Rossby wave as it enters a region of decreasing westerlies. And what happens is that the wave tends to slow down. And so these waves moving from the northern part of Asia into the Western Pacific in the exit region of the jet stream tend to slow down, and they tend to compress up. And if the compression and the distortion is sufficient, the Boreal wave says, oh my God, I can't conserve my potential vorticity. I'm going to become chaos. I'm going to break. So that's in the mind of a Rossby wave. But if anybody's interested, I can point to a number of theoretical studies which support that rather flim-flam argument.
Okay, another question from a student is, while the prediction of the monsoon period, I mean the length of the monsoon is accurate, the same is not true for the intensity. What is the 10 to 20-day oscillations role in this?
Yeah, that's a great question. I think one of our great failings in monsoon meteorology has to think of the monsoon as it rains and stops raining. It starts to rain in June and it stops raining in September. And there's an enormous amount of variability in between. So I think the monsoon, in essence, is defined by its variability. But we do know that in this period from June to September, we're going to get large variations. So I think that these variations make the monsoon. So if we want to talk about the monsoon, we have to talk about its variability. And the variability, Dev Sikar had a nice study, and he and I had a friendly argument about if you were to talk about the monsoon variability, strong or weak from one region to another, I would argue that the monsoon variability from year to year is regionally different. And he had a slightly different argument. He said it depends, of course, on how you average, which is true. I think we all missed Dev, by the way.
Another question from D. Rajan. Is there any relation between diurnal monsoon rainfall variability over India and extratropical dynamics?
I think what you find, if that diagram I had showing the variability of monsoon, the Bay of Bengal spectra, great big peak diurnal, and then we had the biweekly and the intraseasonal. So if you were to just do the spectra for times when there was no intraseasonal variability, you'd find that there's suppression of the diurnal variability. So the diurnal variability is mammoth, but it only exerts itself when the large-scale dynamics say, okay, give me diurnal variability. It's suppressed otherwise. So I think to say something very nice, it's a great question, say something nice about the role of the large-scale dynamics. I mean, I don't think you can look at that diagram and say, oh my God, the most important thing is diurnal variability. But what you can say is that the the bi-weekly variation or the intraseasonal variation in concert with the diurnal variability is very important. Am I clear with that?
Yeah. And another question from a student. Why the Rossby wave breaking takes place only in the Pacific Ocean? What about the Atlantic?
They do in the Atlantic, as a matter of fact. Yeah.
Okay.
But the well, that's a very good question, and let me think about that. We have a major monsoon in the northern hemisphere, which is over Asia. We have a minor monsoon, which is in North America. So Africa, Asia monsoon, and then we have North America. So the great divergent circulation in our summer, the boreal summer, occurs over Asia, and that gives you the strongest jet stream. The summer jet stream over North America, by virtue of that divergent circulation, is much weaker. But there is Rossby waves, and they do break over the Atlantic Ocean, but we don't know how important that is.
Is the potential vorticity transport to the South India region reducing rainfall or enhancing it? Because in the plot which you have shown, 16th July has a negative PV and 22nd July has a positive PV in the year 2008.
Well, it varies on the time scale of these oscillations moving through. If you were to look at the if you were to look at the total variability, those mean charts, as distinct from the variability charts, these things go up and down at different times of the monsoon period. I'm not quite sure I understood the question, but one should look at, here's a great thing for a graduate student to do, is to reproduce those time sections of potential vorticity for year after year after year and examine and see how strong this relationship really is. I mean, hey, this is theory. We found one correlation. It could be right, great, but it could also need modification.
Okay. Yeah. And one question from Ashok. Does it mean that the source of the transient frequency variability, which is transported to the tropics through Rossby wave breaking, lies in the tropics itself?
Lies in the tropics itself? No, because you don't get Rossby waves forming until you have strong divergent circulations in the tropics producing the jet stream. And that gives you the circuit. I think the circuit is the important thing. This is giving me lots of ideas of what I want to work on next. I'd love this talk. Thank you so much for these questions.
Yeah. I have a couple of questions. Do you see any shift in the rain belts during the Indian summer months towards the east?
Do you mean the long term?
Yeah. I mean during the phase of the monsoon, all the 120 days, of late we are getting more rainfall in the Tamil Nadu region, even in the southwest monsoon.
I haven't looked at the variability of precipitation as a function of time beyond those few years that we did.
Yeah.
But that's a very good question. But I think one has to be very, very careful too, that the natural variability of the monsoon from one year to another, or within one monsoon, is so strong that one can jump to the wrong conclusions very quickly. One has to go back. And the great thing about the Indian monsoon and the Indian Meteorological Department is that the data goes back for so long that one can really get into the details of what the variability is.
One layman's question: why the number of monsoon depressions are becoming lesser and lesser during the monsoon?
One of the that's a good question, and I have to admit I haven't thought too much about it. Again, I go back to my friend Dev. our dearly departed Dev. We spent a lot of time on that. But if there are variations, I assume that you're correct. And it's not that we observe things better now than we did in the past. Let's assume that you're what is correct. Then one would think, oh my goodness, the shear must be changing. Because the greatest difference between one part of the monsoon and the other, or between the early pre-monsoon and the post-monsoon, is the vertical shear. So the question would be, is that changing? And then that leads to other questions about why it's changing. But that's the question I would ask first. And I have to admit, I haven't thought about it.
Okay, regarding the westerly duct on the eastern side of the Tibetan High, as well as on the eastern side of the Bolivian High, how can this be used for prediction with respect to Rossby wave breaking?
Well, excuse me. First, it's the place to look.
Okay.
It's a place to test the dynamics that I've been putting forth today. Be I right or be I wrong? You know, the greatest thing about being a scientist is to pose hypotheses and then be knocked over like a bunch of skittles. But yeah, the Westerly duct. I spent 30 years off and on thinking about the Westerly duct from the work I originally did with Jim Holton. It's when you think that the great cloud bands, the monsoons and the Atlantic Ocean, the Pacific Ocean, the communication takes place in these regions of westerlies or higher than average potential vorticity. That is a region that one should look, it seems to me. It's a region of variability. It's a region that needs more exploration, seems to me.
One last question. How far can regional numerical weather prediction models be used for monsoon prediction?
I'm glad that's a final question. I've just finished a paper, which is in the Bulletin of the American Meteorological Society, and it speaks about the use of ensemble prediction in the monsoon regions, which I'm a great advocate for, and I know that the IMD and Pune are working hard in that direction. But what I think one can talk about, and this is such a great question because let's go back to that, the Sikar-Gadgil thing. How much confidence do we have about the intraseasonal variability? We know there's a band across South India. What is our probability that it's going to expand to central India, to northern India? And these are the questions that only come out from because there's such non-linear processes, one has to do the ensemble prediction. And so I think that, you know, there are things that we can do very well with ensemble prediction. The Uttarakhand precipitation disaster, that had 10 days predictability from the environmental the ensemble prediction system. Now, that's no faulting anybody, but it was there. And so what we can say is that we can start forecasting extremes with its ensemble prediction. In terms of the more important thing, really, which is it going to rain in the next 10 days and not rain in the next 10 days? How long is the rain going to last? That's something we have to learn how to use ensemble prediction systems for. I'm writing a paper on that now, so you can ignore everything I say because I'm sure to change my mind.
Thank you very much, Professor Peter Webster, for your elucidating lecture, which will be useful for our student and research community at the Department of Meteorology and Oceanography, Andhra University. Now I welcome my head of the department, Dr. C.V. Naidu, to propose a vote of thanks. Namaskar. Yeah.
Thank you. I have one thing to say, if I could. One tiny thing to say that
Yeah,
if anybody has any questions, because
yeah,
what can you say in half an hour to an hour? I am happy to answer emails and provide answers to any questions that people have.
yeah. Thank you very
If
much.
you can provide my email address, that'll be fine.
Okay, thank you very much, sir. Thank you. Yeah, Dr. Knight.
Okay, I thank all the researchers and the students who attended the lecture entitled Relationship between the Monsoon Variability and Extratropical Dynamics, delivered by Professor P.J. Webster. Professor P.J. Webster is the most prominent researcher and a legend in the scientific community in the world. He is a good human being with a charming personality. We love him very much. His research career has focused mainly on the dynamics of large-scale coupled ocean atmosphere systems of the tropics, notably the Asian monsoon system. Dear sir, as a renowned researcher, your expertise is of great value to the web series. You are role model to many researchers and myself also. We are very fortunate today to hear very enlightening lecture. I should be thankful to you, sir, for giving us an inspiring lecture. Dear sir, there are some promising students and researchers in our Department of Meteorology and Oceanography, Andhra University. I am looking forward for your help in the development of our Department of Meteorology and Oceanography. We pray Almighty to confer more strength and help to you to extend your help and guidance to the present generation students and researchers. Dear sir, you are welcome to our department whenever you are in India. Thank you, sir. Thank you. Thank you very
Thank
much.
you.
Thank you very much. Namaskar.
Namaskar.
Thank
Namaskar.
you. Yeah. Yeah.
Good night.
Uh,
Or good morning.
Late evening for you. Yeah, yeah. Good. It must be 11:30 in the night. Yeah.
No, 8:30 is pretty good. Yeah, yeah. But we expect 10 inches of snow tonight. That you don't get in India.
Thank you.
Good night. Yeah.
Good night.
Good
Good
night.
night.